Section 4.4 is on concavity in the second derivative test. So in section 4.3 we learned increasing, decreasing, maxes and mins. That was actually over the last few sections. But we learned to find intervals of increasing, decreasing, and max and mins. You do a sign chart on the first derivative. So now what we're going to learn is about concavity, something called inflection points, and the second derivative test. And all of this requires that we analyze the second derivative of a function. So again, the second derivative, you just take the derivative of the derivative, and then we're going to do the exact same process, the sign chart. So we're going to set the second derivative equal to 0 or undefined. We're going to create our number line. We're going to determine the test intervals. We're going to test a point for each interval, and then that's going to determine our concavity, concave up and concave down. It's going to determine inflection points, and then we're also going to learn something called the second derivative test, which is gives us the same results as the first derivative test. And if you remember, the first derivative test gave us maxes or mins. So that's what the second derivative test is going to do as well, give us maxes or mins, but instead of using the first derivative, we're going to use the second derivative, okay? So let's get to this section. We're going to start talking about concavity. Let's actually define what concavity of. It says, let f be differentiable on an interval I. The graph is concave up when f prime of x is increasing. So when the derivative is increasing. So the derivative would be increasing when its derivative is positive. So it looks to me like what we have here is concave up means the first derivative, so here's the original function, means that the first derivative is increasing, which tells me that the second derivative must be positive. So the first derivative is increasing when the second derivative is positive. So it's concave up when the second derivative is positive. And then it says it's concave down when the first derivative is decreasing. Well, the first derivative is decreasing, so that's concave down. The first derivative is decreasing when its derivative is negative. Remember, a function is increasing when its derivative is positive. A function is decreasing when its derivative is negative. So we need the first derivative to be decreasing. So we need its derivative to be negative, which would be the second derivative would be negative. So concave up and concave down is determined by looking at the sign of the second derivative, and hence that's why we're going to start doing the sign chart for the second derivative. Okay, it says the following graphical interpretation of concavity is useful. It says let f be differentiable on an open interval. If the graph is concave upward, then the graph lies above all of its tangent lines. So if you think about looking at its tangent lines here, here's its tangent lines. Notice the graph is above it every single time, and if it lies below it every single time, it's concave down. Look, I think there's an easier way to do this, in all honesty. When I look at concave up, it's got to be part of a smiley face. And when I look at concave down, it has to be part of a frown. So concave down is a frown, concave up is a smiley face. If it's the left half or right half of the smiley face, it's concave up. If it's the left half or right half of a frowny face, it's concave down. So those are the shapes right there. And we can get in and we will analyze those a little deeper in the next sections. But for you, that's what you want to know. So if you notice, concave up has a place where it's decreasing, where the function's decreasing, and it also has a point where the function's increasing. So concavity does not mean the function is increasing or decreasing. It could be doing either. Concavity is merely the shape of the graph. Does the graph open up or does the graph open down is what we're asking, okay? So concavity is not increasing and decreasing. Concavity is the shape of the graph. All right, so let's continue. It says to find open intervals on the graph of a function f is concave up or concave down, you need to find the intervals for which f prime of x is increasing or decreasing. For instance, the graph of 1/3 x cubed minus x is concave down on the open interval negative infinity to 0 because its derivative, which is the derivative of 1/3 x cubed minus x, would be 1/3 times 3x squared, so that would turn into x squared. And the derivative of x is just a 1, so the derivative would be x squared minus 1. and it says x squared minus 1 is decreasing there. And then it says, similarly, the graph of f is concave upward on the interval 0 to infinity because f prime of x is increasing on that interval. Look, that's like looking at the graph of the derivative, and I don't like looking at the graph of the derivative. Here's what I would have done on this problem. I would have said, let's look at f of x. So f of x is our original function, 1/3 x cubed minus x, right? So the next step would be find its derivative. And its derivative would be 1/3 times 3x squared. Again, that would be x squared. And then the derivative of minus x is a minus 1, okay? Now let's look at the second derivative. The second derivative is equal to 2x. If we set the second derivative equal to 0 or undefined, which is what we call critical values for the first derivative, or critical numbers, it is not called a critical number for the second derivative. Critical numbers are where the first derivative equals 0. So let's try setting the second derivative equal to 0. It's never undefined because it's a polynomial. Divide both sides by 2. We'd have x equals 0, right? So what we would do is we would look at our number line. We would have x equals 0, and now, 0 there. And we know that the second derivative, we're plugging things into the second derivative now. We know at 0 it is 0. And so what we would do is we would take x values and we would plug it into the second derivative instead of the first derivative now. Remember, the second derivative is 2x. We look at the first interval, which would be negative infinity to 0. And we look at the next interval, which would be 0 to infinity. We need a test point in the first interval, so let's use, how about negative 1? And a test point in the second interval from 0 to infinity, how about positive 1? And when I plug that in, 2 times negative 1 would be negative. 2 times positive 1 would be positive. So I know on the first interval, my second derivative has to be negative. On the second interval, my second derivative has to be positive. Well, anytime my second derivative is negative, that tells me that my original function has to be concave down, the shape of a frown, some part of the shape of a frown. And anytime your second derivative is positive, that means it's concave up. So that would have given me my intervals of concave down, would have been the interval from negative infinity to 0, and the interval of concave up would have been the interval 0 to infinity. So that's how I would have gotten my answer. I wouldn't have looked at the graph of the derivative. I would have done the sign chart for the second derivative. All they're trying to emphasize here is the definition of concavity. How do we know that it is concave up? Well, because my second derivative is, or my first derivative is increasing on that interval. How do I know it is concave down? Because my first derivative is decreasing on that interval. Okay, so all they were doing in their description right here was tying it to the definition, but we don't need to worry about the definition of it. What we like to know is when a second derivative is negative, I am concave down. When a second derivative is positive, I am concave up. So we will always use the sign chart on the second derivative to determine intervals of concavity.